So here's another example of finding the electric field due to a continuous charge distribution. Here I've got a charge distribution that's a long wire or a short wire, it doesn't matter. Let's say it's positively charged with some charge density. So we're going to describe that as our lambda, which would be a charge per unit length. Okay, so our density, when we talk about mass density, it would be mass per volume. This is now charge. Instead of volume, because we're just interested in length, we can just say charge per length. The beauty of that is just like our densities for rocks and things like that. Once we know the density of the material, it doesn't matter whether you have a big rock or a small rock. It all turns out to be the same. Okay, and so I'm asking, it's going to be of length L, so we're going to say this is position L over 2, this is minus L over 2, say in the y-axis. So we're going to say this is in the y direction, and we want to find the electric field right in the middle, and we're picking the middle because that's frankly easier, and this will be complicated enough. So if we look at, say, the electric field due to that little bit of charge, this little dq right here, so this is just following what we've done before, then we can say that electric field points in this direction, and this starts to get at why we would pick the middle, because what we can do is say at some distance, let's say this is y, at an equal distance down here, we can say there's an equal amount of charge that provides an electric field that points up, right? And so altogether, all we need to worry about is the electric field in the x direction. There will be no component in the y direction. So the electric field is only in the x direction. And so that means we just need to find the little bit of the electric field in the x direction due to this little bit of charge here, and then we add that up to find our electric field, our total electric field in the x direction. Okay, so we're going to focus on just this one setup. So we can set an angle here, theta. This is also theta, so we can say, of course, dEx is just going to be dE times cosine of theta, because that's the adjacent angle. This EX points in the adjacent direction. I guess I should keep that in the same color so it shows up. And then we just start trying to see what contributes. Well, to find the electric field, we can say dE is just K, that little bit of dQ that's sitting right here, this little bit of dQ, over R squared. That's it. That's the magnitude of E, that's the magnitude of the electric field, and then times cosine of the theta. So this is our R, which isn't too bad, and we'll say that we're interested in this electric field some distance A away. Okay, just like in the last example, just finding this distance that it is away. So if we look at this, our dE is equal to K dQ. Our R we can write in terms of this A, which would be a constant, and Y, which would change, right? Y would go from 0, and we would actually add up all the contributions as Y goes from minus L over 2 to plus L over 2. So this would be A squared plus Y squared, just using our Pythagorean theorem to find this distance R. So then our dE in the x direction is just going to be K dQ over A squared plus Y squared times cosine of the angle. And then what we're going to want to do is integrate this. And of course, this is where it gets not so tricky. It's just we've got a whole bunch of variables and what's changing and what's not changing. And notice as we go to different points on this, so as I go to a different point, I'm changing my y value, right? My y value is different at this point compared to this point up here, and my angle is also different. So my variables are really, I've got y and theta, but I've really got one integral. And I would like to make it y, because then I could say my limits of integration would be from y is equal to minus L over 2 up to y equals L over 2. So I want everything in terms of y if I can. And then of course I've got this dq that I need to deal with. So my goal is to figure out how to write that in terms of a y, because that looks like a variable and I need a dy, and how to write that in terms of y. So we'll start with the cosine. So cosine of theta, so that's this, that would be the adjacent over the hypotenuse. So that would be a, which is not y, over r. But r, we know from the Pythagorean theorem that we can rewrite this as a over the square root of a squared plus y squared. And that's not bad because I've got it in terms of the constant a and y. So that's a start. So that gives me this is equal to that. So I can put that right there. And then I just need to deal with my dq. And that's where my density comes in, because I know that my density is capital Q, the total charge, over L. But it's also, because it's any little piece, it would be dq over any little distance, right? Like this little height, which I can call dy. That's my little height there, right? So dq over dy. So I can rewrite this to say dq is equal to lambda dy, where this lambda is a constant. It's however much charge per length, 4 coulombs per meter, 10 to the minus 6 coulombs per meter, whatever that charge density is, charge per length is. That's just set by however many plus charges I have, depending on how long that is. So I can substitute this right in there. So putting those things in, I'm going to have integral dE in the x direction is equal to then integral k. I'm going to put in, for dq, I'm going to put lambda dy all over a squared plus y squared. And now for cosine of theta, I'm going to put this expression. So that's going to be an a over square root of a squared plus y squared. It's not looking very friendly, but it's something that we can do. So what we can recognize is that this is just ex, right? Integral of a derivative is that value. That's what the fundamental theorem of calculus says. This gives us, from our y values, remember we're going to integrate from y equals minus L over 2 to plus L over 2. So that's minus L over 2 to plus L over 2 are my limits of integration. And then I've got k a lambda dy, and then this is a squared plus y squared to the first power. This is a squared plus y squared to the 1/2 power, so I can write that all as a squared plus y squared to the 3/2 power, right? Because 1 plus a half is 3/2. Now I can just pull out my constants, right, out of the integral, and then we've got an integral that's maybe not the most friendly integral we've ever seen. So I've got k a lambda. I've got this integral from minus L over 2 to L over 2 dy over a squared plus y squared to the 3/2 power. Now, in Calculus 2, you learn how to do these integrals. You do a trig substitution, but once you've learned how to do it, then you can just look it up. And Wolfram Mathematica is your friend as far as that goes. So we're looking for this integral, and so all we do is just type it in. So I've already pulled it up. I've gone to Wolfram Alpha, and you can see that I've typed in, I want the integral of a squared plus y squared raised to the minus 3/2 power, right, because it's 1 over 3/2. And just so I know that it's the right one, Wolfram rewrites this for me. It's there. And then this is the value. So it's y divided by, they did the indefinite integral because I didn't give the limits of integration. So that's the expression. So we're going to put that in and just copy that straight over. So these are the constants that I carried right here. And then this is what I copied from Wolfram Alpha, but I've got to then take my limits of integration. I can do a little bit of simplification. Notice that this 1a cancels there. And then I'm going to substitute these limits of integration in for my y values. So that is going to become ex is equal to k lambda over a. These are the constants. And then I'm going to substitute L over 2 over the square root of a squared plus L over 2 squared minus, now I put in my other limit of integration, negative L over 2 all over square root of a squared plus minus L over 2 quantity squared. Now, these are both the same denominator because once you square, that negative sign goes away. So this becomes k lambda over a, and this becomes a plus, so everything is quite nice. I get L over 2 plus L over 2 added together. They've got the common denominator. So that just becomes L over the square root of a squared plus L squared over 4. Okay, and that's our answer. Great. Tells us a lot. That is the electric field at this point. That tells us how big it is. So, in fact, we can say that the electric field right in the middle of a wire, right here, when we're a distance A away from that wire, then this is the electric field. And it points in the X direction. It doesn't have any components in the Y direction because we set it up. This is L over 2 and this is minus L over 2. Now we can actually think about if we have a really long wire. So if we send L to infinity, so we take that basically the limit of this as we send L to infinity. Notice we've got an L up top, that's going to infinity, and an L in the denominator, that's going to infinity. So we can actually rewrite this just a little bit. So I've got an EX is equal to K lambda over A. I'm going to have an L, and I'm going to factor an L out of this, an L squared. So I get an L squared, A squared over L squared plus 1/4. This is all to the square root, right? So that's just the same expression, okay? But this L squared can now come out of the square root and become an L. The other stuff has to stay in there, of course. And so those cancel. And now, as I take my limit, as L goes to infinity, this works much better because this term is going to 0, right? I've got an A squared over an L squared. Let me zoom in on that. As this gets very big, that turns that into a 0. And so this becomes K lambda over A times 1 over square root of 1/4. And so that just becomes square root of 1/4 would just be a 1/2. I get K lambda A times a 1/2. So that becomes then 2K lambda over A. And so that's the electric field if I have an infinitely long wire. Now, of course, we can't have an infinitely long wire, but we can have a very long wire. And what we're going to do is head into ways to solve these types of situations, like the very long wire. We're going to redo this. And what I hope I can convince you is a much easier method than setting up this integral, right, and then having to look it up. I mean, the hard part of this, honestly, is trying to set up this integral, set this up, set up your integral correctly, figure out what variable you're going to focus on, and then make the right substitution so you can actually do the integral. Because once you get to this point, then you're just looking up the integral somewhere if you don't know how to do it. And that's perfectly fine when you're doing this kind of homework. Okay, but I'm hoping that I'm motivating you to let's find an easier way to do this. And so that's what we're going to introduce with Gauss's law. It will take a little while to get there, but I hope you'll be motivated to be interested in doing that so you can avoid some of these steps that you've seen here.